The filter is a component which removes the contaminant from the compressed air. The three types of contaminants present in the compressed air are solid particles, water, and burnt oil. Why do we need to remove each type? Firstly, the solid particles pose a threat for the good functioning of the pressure regulator, the valves, and the seals. In the pressure regulator, they can cover capillary tubes, therefore rendering the component useless. In valves, they can gunk up with the lubrication present in the spools or poppets, slowing down or even blocking their movement. And finally, in cylinders, the solid particles also pose the threat of gunking up together with the lubrication, leading to resistance in movement, causing inefficiencies. 2. Water condensate. It leads to premature wear of the seals by washing away the lubrication inside the cylinders and valves. If the temperature of the environment drops below the freezing point, it can also ice up inside, blocking moving parts. And finally, the burnt oil attacks the rubber, therefore deteriorates all gaskets it comes in contact with, reducing the life of the component. This is the only contaminant out of the three that isn't found normally in the air, but it is introduced into the pneumatic air by the compressor. At this point, our pneumatic air is already pre-filtered by the main line filter, which is present at the centralized preparation stage. Most of the water is also taken out up to this point, by eliminating it when condensed in an air tank, tube network, and in heat exchangers. The oil is usually sticking to the filter element in regular air filters, but if there is a need for more, manufacturers have developed specialized filter elements. Now, let's see how does a regular air filter work. Air comes in through the in port on the left. When it comes in, it gets a spinning effect from a piece called the deflector, which is fixed and has angled fins. The spinning effect helps at getting rid of bigger solid particles and water drops, which are thrown on the walls of the inner bowl. Afterwards, the air goes through the filter element from outside in. Here, the smaller particles, which weren't thrown on the walls of the bowl, are getting stuck in the element. The air pad end goes from the middle of the filtration element to the outport. In the middle of the bowl there is a baffle, which separates the spinning zone from the calm zone, where water and big particles collect to be expelled by the drain. The drain can be manual or automatic. The manual one needs occasional observation, and the automated type will drain itself when the water reaches a certain limit. Let's take a look on how the automated drain works. There are actually two construction types, normally closed and normally open. First, the normal closed auto drain. It has this ring-shaped float, which will be raised by the water due to the buoyant force. The float operates a lever, which in turn opens up a simple valve, which regularly blocks the small air path. When it opens, air rushes in, pressurizes the chamber, and pushes a small piston against a spring. When moved out of the way, the piston opens up readily a flow path for the water. The water rushes out, encouraged by the pressure inside the bowl. To close back up, the piston has a capillary orifice through which the pressure can escape. This orifice is very small in diameter, letting air bleed out slowly, keeping the piston open for a little while, 3-4 seconds, giving enough time for the majority of the water to escape the bowl. It is called a normal closed auto drain because unless the float rises, it will not let water escape. This can become a little problematic in certain situations where the machine is not in use for a while and water just stagnates inside. In comparison with the normal open auto drain, it has this disadvantage. Now, let's see how the normal open auto drain works. This auto drain, unless pressurized, will stay open, letting water drain out. When the system receives pressure, it will close and work exactly the same as the normal closed one. The difference is that the piston inside the normal open is held open until pressure accumulates in the ball and pushes the piston against the spring. Then, when the valve at the top opens, pressure will rush in to aid the spring, pushing the piston down. Afterwards, as before, upon water drainage, the valve will shut, and through the capillary orifice, air will bleed out slowly, keeping the piston lowered for a little while to give water enough time to fully drain. Finally, the pressure will rise the piston back to close the water drainage path. As this design requires a certain pressure to operate, the disadvantage with the normal open auto drain is that at the system pressurizing stage, if you use too many of them, the compressor might not keep up with the initial air leakage. But, as discussed before, it will keep our air filter drained at all times, when in use or not. Now, for the symbol. The symbol for the air filter is simple. We'll start with a rhombus, after which we have to symbolize a in and an out port. Now we have the standard symbol for a passive pneumatic component. There are multiple types of filters, differentiating themselves mostly by the filtration level they can achieve, but also by the drain type. So, continuing from the rhombus, with a vertical dotted line, we have the simple filter. If we are doing two dotted vertical lines, now we have a microfilter. If we go further and draw three dotted lines, we have a sub-microfilter, which removes even the smell from the compressed air. In terms of drain, a horizontal line, 3/4 down from the top, symbolizes a manual drain. If we draw another triangle inside, it becomes an air filter with auto drain. When powering a pneumatic cylinder, the most important aspect we need to consider is output force. Let's say we have a compressor, which gives us 1 megapascals, 10 bars, or 140 psi. When we use some of that accumulated pressure, it will slightly drop. If we have a large number of pressure actuators and air blowers, the pressure will drop significantly. And even if the compressor works continuously, it will have a hard time compensating. So we will have to design our machines and systems to work at a lower pressure than the output of the compressor. Somewhere between 0.5 to 0.7 megapascals, 5 to 7 bars, or 70 to 110 psi. Let's take the common pressure of 5 bar. In the compressor tank, we store 10 bar of pressure, which we know now it is too much. This is the function of the pressure regulator, to bring a higher pressure down to a stable lower one, which can also be sustained by the compressor. Also, the air compressor isn't working non-stop. It raises the pressure. After a threshold, it stops, let's say 8.5 bars. It starts again, building up to superior pressure, and so on. This is another important function of the pressure regulator. It keeps the pressure stable on the output to the cylinders, even if the input varies, as long as the variation doesn't go too far below a certain point. To understand this quicker and easier, imagine that everything before the pressure regulator, to the left side, air tank heat exchangers tubes, are a tank of pneumatic air. And let's also imagine that about the other side, all cylinders, tubes, valves, and so on. In this animation, the indicator is showing us the out pressure. We should also keep an eye out for the reading. The main valve on the top opens and closes the air path according to our adjustment. When we rotate the screw, a spring compresses and pushes against the main valve with a rigid disc. This action lets air go from the in port to the out port. After a while, the valve gets closed back up. The rigid disc is radially attached to a membrane, which separates the lower part into two zones. On the membrane, there is pressure pushing back against the spring. This pressure is coming through a capillary tube from the out port. Right now, the force of the spring and the force of the pressure on the membrane are balanced. If consumption starts and cylinders actuate, the pressure lowers. Think of it like there is a small bleed hole in the imaginary tank on the right. Then, the pressure force on the membrane lowers and the spring can push on the rigid disc to open the valve. This opening will balance at a certain point in such a way that it keeps the pressure steady at the out port. If we take a look at the gauge, we'll observe the pressure stabilizes itself lower than the 4 megapascal setting. This is an indicator that for the pressure regulator to provide us with the needed setting, we must set it while the consumption is taking place, not at rest. The last thing to know about the pressure regulator is that when you lower the pressure, or we even go as far as shutting it, on the imaginary right tank, there will be a higher pressure than the setting. This, in turn, will push the rigid disc further against the spring, and the entire pressure present in tubes, valves, and cylinders will be exhausted through the center of the disc to the atmosphere. This is called the pressure regulator relieving type. There are also non-relieving pressure regulators, but rarely they are used. The only reason for which to use a non-relieving type is when the gas is not air and is poisonous like carbon dioxide or combustible like methane. The symbol is not hard, but is the one that gives beginners the most problems. We start with a square. We symbolize an in and an out. Now, following the exact functioning of the regulator, in the middle there is a membrane on which a spring acts from the top, which is adjustable, and on the other side there is pressure acting in a feedback loop, coming from the out port. If it is the relieving type, then it also has a triangle on the side to show it exhausts air to the atmosphere. To maintain good working pneumatic components, there is the need to create a film lubrication between the moving parts. Friction in every mechanical system is an enemy. You can try this little experiment. Rub a pencil rubber on the desk and see how it feels. Then try to wet the desk and rub it again with the pencil rubber. Try to apply the same vertical force to be easily comparable. We can obviously feel the difference. It not only reduces the friction force, but because of that, the wear and tear lowers. This component in today's industrial environment is not necessarily needed anymore. Some manufacturers provide all their cylinders pre-lubricated for life. They use the petroleum jelly technology borrowed from aviation industry, which is very high performance, but if you use the lubricator on those cylinders, you will wash away the high performance lubricant and you will need to carry on with using the lubricator going forward. Let's take a look on how the pneumatic lubricator works. The assembly comprises a body which has a straight air path but with a rubber flap. Most of the air flows directly over the bent flap, but in the process the flap gives the airflow some resistance. This resistance is small and it will direct the air into the oil bowl beneath. There, like in a hairspray, pressure will push liquid up the straw through a screw adjustable cross-section. This is used to adjust the number of oil drops we want the air to take. On the top, there is a see-through drop channel to be able to supervise the operation. One caution this component has, and you really have to be careful about it, is the need of turning off the pressure when refilling. The symbol is simple. It starts with a rhombus, which has a line at the top that represents the drop channel. It also has the in and out ports.